we rewrite our circuit. It's actually the exact same circuit. Nothing is changing here. We have a resistor and an inductor, and we have a voltage source connected to this resistor and this inductor. And so the value of the resistor, in this case, R, is equal to 4 ohms, and the inductance of this coil is equal to 2 henries. So just some values of things you'll buy off at the store. And this is V of t, function of time. But in this case, we're going to say that this voltage here, V, is actually going to change with time. And it's going to be a cosine of 3t. So that's a very, very important change. It's a very, very important change. It's a little innocuous looking change, but it'll actually have a pretty large impact later on. Now, just to kind of draw a comparison here, the last circuit we did was almost exactly the same. Values were a little bit different, but for the voltage, we had a constant steady state 12 volts. Just shooting current in one direction constantly through this, this voltage that never really changed. It was like hooking a battery up. This is more like hooking your wall outlet up, although the frequency isn't quite the same. It's the same concept. The voltage is going to be swinging back and forth constantly here. So it's going to yield an answer that's quite different than the previous one, simply because the input source is behaving totally differently. It's kind of throwing the voltage up and down all the time, which is going to cause the current to go up and down all the time. And remember, we already talked about the fact that this inductance reacts to current changes, and voltage across that inductor is going to depend upon how fast the current is changing with time. So it's going to yield a solution that's going to look a little bit different. But the beauty of circuit analysis, especially when we talk about differential equations, is that although we know the end result is going to look totally different than what we've done before, the process is actually the same. So let's go down this exact same process that we did last time and just see how the math falls out differently rather than stress out about it. So let's go ahead and do that now. What we're going to have is we already know that because of Kirchhoff's voltage law that we talked about in the last section, that the voltage across this resistor at any given time plus the voltage across this inductor at any given time, when you add them together, has got to be equal to the voltage of the source. So if we want to write that down, that would be V of t is going to be V across the resistor plus V across the inductor. I'll just call it IND. I did coil in the previous section. It's inductor. Either way, same thing. So the voltage across the resistor plus the other guy is equal to the voltage of the source. So let's do that. What is the voltage across a resistor? V is equal to IR. We learned about that in the last section. That's Ohm's law. V is equal to IR. So the voltage across here is I times R. Okay? Plus the voltage across this we already talked about. It was L di dt. We haven't put any values in. We're just doing the general circuit. And that's going to be equal to, because we add them together, it's equal to the source, V of t. This is in fact exactly what we wrote down at the start of the last problem. There's no differences because we haven't really put any values in anywhere, and the circuit's really the same. So let's put some values in now. R is 4, so we have 4 times I plus L is 2, so we have 2 times di dt, and that's going to equal to the source, which is cosine of 3t, because that's the voltage across the terminals there. So this guy, this is the non-homogeneous equation. Non-homogeneous is a fancy word that means behavior of the system when we include a forcing function, a source hanging on the end, pushing, in real time with some kind of energy input. And that's what this is representing here. So we have the system here represented by this stuff. We have the source here represented by this stuff. So the first step to solving this equation is to remove the source and just see how the system behaves. And we, in differential equation language, we call it solving the homogeneous version of that differential equation. So we want to solve the homogeneous version. H is homogeneous, which is 4 times I plus 2 times di dt is equal to 0. So this looks like very, very similar to last time, and in fact it is very similar. So let's go ahead and look at this. This is a separable differential equation. So let's move 4i over here. So we'll have 2 di dt is equal to negative 4i. Of course, we can divide both sides by 2. So what we're going to have is di dt is equal to negative 2i. We just divide both sides by 2. And in order to actually get anywhere, we need to move the 2i over here. By the I, we need to move the dt on the other side so we can integrate both sides. So what we're going to have is negative 1/2, and I'm going to go ahead and write it as 1 over I di is equal to dt. And you may do it a little bit differently on your paper, but basically I'm doing the same thing. I'm dividing the negative 2, I'm getting negative 1/2, I'm dividing the I, getting 1 over I, di stays here, dt gets multiplied, moved to the other side. So now I can integrate both sides of this guy. I'm going to have negative 1/2 times the integral of 1 over I di is equal to the integral of dt. So I'm just integrating both sides. Of course, this is a constant, so he comes out of the integral. And what I'm going to have over here is negative 1/2 times the natural log of I is equal to t, this integral, plus some constant of integration. I don't know what it is yet. So I'm just getting this natural log. So up until now, things are really similar to before. And so when I complete jockeying around with this guy, let me move the 1/2 back over there and kind of get things isolated. I'll have natural log of I is equal to, multiplying by negative 2 over here, I'll get negative 2t plus a constant. The reason you don't have 2 times constant is because you're multiplying a constant by a number. You're just going to get another constant. So anytime you're doing that with these arbitrary constants, you can just forget about the multiplication. It just wraps back up in the constant. So when we do this, we get natural log of I is equal to 2 times t plus a constant. And what we're going to do next is raise both sides to the power of e. So we'll have e to the natural log of I is equal to e to the negative 2t plus a constant. So all we did was take this guy and raise both sides to the power of e, which is what we get over here. The reason we do that, let me try to work a little bit horizontally because this problem is going to get lengthy really quickly. So what we'll have over here is I is equal to, because I drops out, over here we're going to have e to the power of c times e to the negative 2t, right? Because we just rewrite this as a multiplication, because we can add these exponents here, which we can also rewrite. Let me switch colors again just to make it totally clear. I is equal to k times e to the negative 2t, because I'm just rewriting this constant as a value k. So what we have here is I of t is equal to k times e to the minus 2t. This is the solution to the homogeneous version of the equation right here. What this is telling you is, if I take away the source, if I take away the cosine here that's driving everything, and I just sort of look at the system response, this is what I'm going to get. I have an arbitrary constant because I don't know what my initial condition is, but if I just shoot some current in there and then let go of everything, don't touch it, don't put any more in there, and then just see how the system responds, what this is telling me is the current is going to start at some value and then decay, just like the last problem. So up until now, really, things have been very, very similar. It was a little different up here because I had different values, but it's effectively exactly the same as what we did in the last section, which is why I presented that problem first instead of this problem first. All right, so the next thing we need to do is, so I'm going to put a little star by this because this is kind of important, although this is not the real solution that we seek. What we want to do now is we want to vary the parameter. The parameter k. In other words, we're doing variation of parameters method. That means that we get a homogeneous solution and we just assume that the actual current is going to vary like this, but k can be made to vary with time. So when we do that, we're going to get a new I of t that we really think the real solution is, which is going to be this k varying with time times e to the negative 2 times t. Okay? So what we need to do to make progress is take this actual solution form that we think we have and plug it in to our non-homogeneous full-blown equation with the source and see if it becomes solvable. In other words, see if we can solve for what k is, which we will, you know, because I've done this problem before. And it is going to get a little ugly along the way, but you know, we'll get there. So in order to plug I in, we're going to plug I in here, but we're going to need di dt. So let's calculate di dt. And I'm going to do that probably here. So di dt. This is a derivative, but we have two functions of time. So you're going to do the product rule, k of t times the derivative of this, which is negative 2e to the minus 2t, plus this e to the minus 2t times the derivative of this, k prime of t. Make sure you understand that just so that you can save yourself a little bit of heartburn later on. So you've got this times the derivative of this plus this times the derivative of this. Of course, you don't know what the derivative of k of t is, so you just leave it as a prime indicating that it's a derivative. Okay, so let's go ahead and let's draw a little line here. Let's plug in to the non-homogeneous version of the equation, which is my original equation here, which is 4 times I plus 2 times di dt is equal to cosine of 3 times t. This is the non-homogeneous guy. All I'm doing is writing it down for you again so that we can see what we're plugging into. So I is going to go here, di dt is going to go here, and hopefully we'll get some cancellation. So let's start way over on the left. 4 times I, which is this guy, so we'll have 4k of t e to the minus 2t, that's this part, plus 2, open up a bracket because I've got a large term here. Now this guy, I'm going to write it as negative 2k t e to the minus 2t. Negative 2 comes out front, k is here, e to the minus 2t is here, plus this stuff. I'm going to rewrite k prime of t first, k prime of t e to the minus 2t, close the brackets, equals the stuff on the right-hand side, cosine 3t. Cosine 3 times t. All right, so I just barely made that on the board. Let's go ahead and expand this multiplication here. So you have to do a lot of writing in differential equations, unfortunately. There's no quick way around it. I guarantee you, if you start skipping these steps, trying to do things in your head, you're just going to get the problem wrong. What we have, 2 times 2 is 4, but it's negative 4. So we have negative 4k prime of t e to the minus 2t plus this guy. 2, don't forget 2, so we have 2 times k prime of t e to the minus 2t is equal to cosine 3t. Make sure you understand where everything comes from here. Really, the only thing is we multiplied 2 to each of those terms. And look at what we have here. 4 times this stuff minus 4 times the same stuff. So we get a nice big cancellation. When you're doing variation of parameters, you really always expect at that step when you plug it back in to get a big cancellation of terms. If you don't get that, you've probably done something wrong. You have done something wrong. So we're left with this. So let's write that down. We have 2 times k prime of t times e to the minus 2t is equal to cosine of 3 times t. Now ultimately what we're trying to do is solve for k prime of t so that we can find k of t so that we can find the whole solution. So let's solve for this guy. What we're going to have is k prime of t is going to be equal to, now work with me here, 2 divided by 2, so we're going to have 1/2 on the other side. All right, actually, you know what I want to do? I want to write this in a different color just to make sure so that it helps me and it helps you. So what we'll have is k prime of t is equal to 1/2. Now when we divide both sides by e to the minus 2t, we're going to get e to the positive 2t. And then on the other side, we're going to have cosine of 3t. Make sure you understand everything going on there. What we have is k prime of t is equal to 1/2 e to the 2t times cosine 3t. And that's equal to k prime of t. So now what we have to do, ladies and gentlemen, is integrate this. So what we have to do is integrate this. So k of t is equal to the integral of 1/2 times e to the 2t times cosine of 3t, and this is dt. Now, if you have a magic button in your head that you can press and get this integral, then you're done, all right? Up until now, really, it hasn't been a whole lot different than the last section. We had a problem, we took away the source, we found the homogeneous solution, which was really the same solution with some constants different. And then we let the parameter vary, we plug it back in, we get giant cancellation, we get this guy, we're ready to integrate. And now all we have to do is integrate to find k. Once we get it, we stick it right back into our solution that we found, and then we're done, right? That's the actual answer. Now here is what often happens in differential equations. You get to this point, you're feeling pretty confident, you get a good cancellation, and you're ready to rock and roll and get the final answer, and then you look down in here and say, I have no idea how to integrate this guy. And then your heart sinks, especially if you're on a test, because you don't have that much time to figure it out. So that's what you have to do. And unfortunately, that's just the truth with differential equations. You really do have to be pretty good with calculus. So sometimes in differential equations, we just have to roll up our sleeves and get good at integration. And a lot of times is what it comes down to. So what do you see when you look at a problem like this? If your teacher lets you use a table of integrals, I guarantee you this is in a table of integrals somewhere. You'd be able to figure it out. If you're able to use a really high-powered calculator or computer or something for homework, you can integrate it that way. Most of the time, you're not allowed to use those things, so you have to use, your techniques of integration. Now, usually, if you had, like, instead of this cosine, let's say the cosine wasn't there. If the cosine wasn't there, this would be pretty easy to integrate. I know how to integrate an exponential. If I cover this up, I know how to integrate a cosine pretty easily. That's pretty easy. And even if I had, like, instead of cosine 3t, if I covered this up, if I had like a t out front, 1/2 t times e to the 2t, I would use integration by parts. Integration by parts I always teach in my calculus courses. You really want to look at using it when you have two things multiplied together. One of them is indestructible, like the exponential. When I say indestructible, I mean that you can keep integrating it over and over or differentiating it over and over and you never get rid of it. Along with something out in front that is destructible. And when I say destructible, I mean you can take derivatives of it over and over, and eventually, like if you had t squared out here, I can take the derivative of t a couple times and get rid of it. And that is going to allow integration by parts to work. But in this case, we don't have either of those things. We have an indestructible function and multiplied by another indestructible function. So integration by parts at first glance is not going to work. But if you remember back a few sections ago, I believe in variation of parameters, I showed you, I hate to call it a trick, it's not really a trick, but it kind of is a trick, to get around that. And you will not get good at it until you just do a few problems that require it, and then you'll remember it. So don't feel bad if you don't get this right away, but basically what we have going on here, we can do integration by parts 2 times, and that will allow us to solve for the answer, because even though both of these are indestructible, when I do integration by parts twice, what you'll find that happens is I can construct my solution so that I can kind of get around the fact that one of them is not destructible, so to speak. And I can solve for the integral I'm trying to solve for, almost like an equation, and we talked about that before. So what we're going to do now is we're actually going to do integration by parts twice. And it's a little bit of a pain, but we're going to get it done. All right, so let's go ahead and rewrite our problem here. We have k prime of t is equal to the integral of, and actually what I'm going to do is I'm going to write it as 1/2 times the integral of e to the 2t times cosine of 3t dt. All I did was take the 1/2 that's sitting out in front here and I pulled it outside the integral. This is the integral we really need to solve. Now, in order to do integration by parts, what we're going to do is set u equal to this. U is equal to e to the 2t. And dv, we're going to set equal to the rest of it, which is cosine 3t dt, right? And so what we're going to do then is just do integration by parts just like you would imagine. So we'll have du is equal to, what's the integral, what's the derivative of this? It's 2 times e to the 2t dt. You just take the derivative of this, but then it's times dt because we really don't know how t varies, so we just have to keep it general. So go back to calculus if you're not quite sure how to do that. When you set your u, you take the derivative of it. You can think of it, saying it another way, du divided by dt is equal to this. You can move dt on the other side. It's however you want to think about it. But this is du, right? And v is going to be the integral of this guy, because we have dv, so we want to solve for v. So what's the integral of cosine? 3t. What you're going to find is that's 1/3 times the sine of 3t. 1/3 times the sine of 3t. This is going to require you to know how to integrate the cosine of something. You could do a substitution here. I have it memorized. I know that the integral of cosine is sine, and I know that I'm going to have to take 1 over the derivative of the inside. However you like to integrate, go ahead and integrate to get that. So we're going to need all 4 of these pieces of information in order to proceed. So let's go ahead and do that now. When you do integration by parts, the equation is u times v minus integral v times du. U is equal to this, so what we're going to have is e to the 2t times v, which is this stuff, so we're going to have multiplied by 1/3 sine of 3t. So u times v minus the integral of v, which is 1/3 times the sine of 3t, times du, which we found here, which is multiplied by 2 times e to the 2t dt. So, see what I mean? It's getting a little bit ugly and we haven't even gotten very far. But that's okay. My advice to you is to keep rewriting the whole line over and over again until you simplify it. Otherwise, you're just going to make a mistake. So here we have 1/3 e to the 2t times the sine of 3t minus, we have 1/3 times 2. That's going to give me 2/3. I'm going to pull it outside the integral. 2/3 times the integral. Now, just to keep it consistent, I'm going to write the exponential in front. E to the 2t times the sine of 3t dt. So what we have is 1/3 e to the 2t sine 3t minus 2/3 integral e to the 2t sine 3t dt. What a mess, okay? And we haven't even gotten to the answer yet, because notice that what this is equal to, just to make sure we're all in the same place, let me change colors here. Everything we're doing is the integral of this guy right here, this integral. The 1/2 is still sitting out there. We're trying to find this integral. What we have said is this integral is equal to this whole mess here, which has another integral. Now, normally when you do integration by parts, the whole point of it is so that when you get all done with this, this is a trivial integral to do. Maybe it's like if you're doing an elementary problem in calculus, this integral might be integral of t, or integral of cosine, or something really easy to do the integral of. But we look here and we don't think we're making any progress because we have an integral here that's basically just as hard as the original integral that we have. We have an indestructible function and another indestructible function, meaning that I don't think I'm going to make any headway. But the trick here, so to speak, quote unquote trick, is that if I don't give up, if I do integration by parts again on this integral right here, notice what happened. When we did this guy, we get some junk out front. Okay, fine, this is part of the answer. The integral that we're left with is the same thing that we had to begin with, and all we did was flip the cosine back into a sine, which is, you know, flipping around because they're derivatives of one another. So if you kind of use a hypothesis here, one would think that if I do integration by parts on this piece right here by itself, then what I'll end up with is this times the cosine 3t, which is back what I started with. So basically by doing integration by parts twice, what I can hypothesize is that my final integral in the very end of it is going to be the same as the one I'm solving for. And so then I can use algebra to solve for the integral I'm trying to find, which is this one up here. If that isn't totally clear, it's okay. We're going to handle it right here. So let's do integration by parts again. Same u, same dv. U is equal to e to the 2t. dv is equal to this guy, sine 3t dt. All right? du is exactly the same as before. du is equal to 2e to the 2t dt. And I've run out of room a little bit for dv, so I'm just going to kind of write it down here. Integrating this guy to get v, what is the integral of sine 3t? It's going to be 1/3. What's the integral of sine? The integral of sine is negative cosine. So I'm going to have negative cosine 3t, like this. So in other words, v is going to equal negative 1/3 cosine 3t. So in order to do anything with integration by parts, I'm going to need this, 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 and this. And to do this integration, do it any way you like. This is a simple integral from Calculus 1, but basically you could do a substitution for u. I just happen to know that if I integrate it and take 1 over the derivative of the inside, that's how I'm going to get the answer. So at that point, I'm ready to do integration by parts again, and I'm going to pick a different color over here. Let me kind of draw a little divider here, like this, because I'm basically going to run out of board space here. So trying to do this integral over here, I've got uv minus the integral v du. U is this, so I have, actually let me switch colors. U is this guy, so I'm going to have e to the 2t times v, which I've got down here, minus 1/3 cosine 3t, okay, that's uv, minus the integral of v, which is this guy, negative 1/3 cosine 3t, times du, which is this guy, which I'm multiplying by 2e to the 2t dt. So what I have here, uv minus the integral of v times du, doing all this stuff again. Now let's take our time and simplify what we have here. So what we have here is negative 1/3 e to the 2t times cosine of 3t. Okay? Now I have a minus, but I have another minus, so what I have is a plus, and I have 2 times 1/3, which is going to be 2/3, times the integral, I'm writing the exponential first to keep it consistent with everything else I've been doing, times cosine of 3t dt. So just to make sure I'm correct here, I have negative 1/3 e to the 2t cosine 3t plus 2/3 integral e to the 2t cosine 3t dt. At this point, it's just getting to be, almost unmanageable as far as how ugly this thing looks. But actually, we're really close to the answer. Notice that once we did integration by parts, again, what we got was exactly what we hoped to get. We have the same function that we have in our original problem, and cosine 3t is exactly what we have. So in other words, we do integration by parts twice. We get a lot of junk out front, but what we end up with is an integral on the end that's exactly the same as the integral we're trying to solve for. So if you ever get in a situation where you do integration by parts 2 times, and on the second time, the integral you get at the end is exactly the same as what you've started with, then you actually have solved the problem. You just may not realize it yet. So let's go ahead and do that now. In order to do it without making a mistake, the best thing to do is to rewrite everything. So don't forget that what we have here is this integral. So I'm going to rewrite it. The integral that we're solving for is e to the 2t cosine 3t dt. That's what we're actually trying to do integration by parts to solve for. Now we did integration by parts the first time, we got this thing. So don't forget this is actually part of our solution. Don't worry about this 1/2 yet, we haven't gotten there. We're just talking about the integral. We have this. So we have 1/3 e to the 2t times the sine of 3t, okay? And what we have is minus 2/3 times this junk, which came out to all of this. But if I try to write all of this here, this is just going to be kind of a nightmare. So what I'm going to do is I'm going to take this guy. It's minus 2/3. So what I'm going to do is write it like this. I'm going to write it like minus 2/3 open bracket, and then I've got all of this stuff. So I have negative 1/3 e to the 2t cosine 3t plus 2/3, I still might run out of space, plus 2/3 integral of this stuff. Integral e to the 2t cosine 3t dt. Look, I didn't run out of space. Okay, and all of this stuff is enclosed, just to make it absolutely clear, since we have the luxury of colors, we're going to put little colored brackets so that we can keep it straight. So what we have is the integral we're trying to find is equal to this stuff minus all of this stuff, and we just have to crank through it and write it and distribute this 2/3 in order to make any headway. So let's do that. Let me go ahead and draw a little divider line so we don't get confused. And let's go ahead and use red. So what we have is, just to rewrite everything, e to the 2t times cosine of 3t dt is equal to 1/3 e to the 2t from up here sine 3t. Okay? And now what I'm going to do is distribute this 2/3 in for this first term. So I've got negative times negative gives me positive. 2/3 times 1/3 gives me 2/9. So I have 2/9 e to the 2t cosine 3t. Okay, cosine 3t. I'm not done yet. I've got to multiply this times all of this. Okay, so I've got negative times positive gives me negative. So I've got negative 2/3 times 2/3 gives me 4/9. So I've got 4/9. This times this gives me 4/9 times the integral of e to the 2t cosine 3t dt. And believe it or not, we're almost to the answer. Now look at what we've actually got here. We have integral e to the 2t cosine 3t dt is equal to 1/3 e to the 2t sine 3t. Just double checking before I get too far. What we have is all of this is equal to all of this junk. But look at what we have. We have another term on the right-hand side with exactly the same integral that we're trying to find. So if we algebraically, forget about calculus. If this were just an equation, x is equal to some stuff, minus x. Or if in this case, we have coefficient of 1 and a coefficient of 4/9. If I take this and I just add it to both sides, I can join it with this term, and then I will have my integral equal to some stuff on the right-hand side. And that is exactly what we need to do. So let me ask you a question, just so I don't have to do it on the next page. If I have 1, and I want to add to it 4/9 of something, because these terms are the same, because I'm going to add 4/9, what's that answer going to be? Well, to get the common denominator, I'm going to have 9/9, right, plus 4/9, right? So 9 plus 4 is 13, so I'm going to have 13/9. So on the left-hand side, what I'm going to actually have when I add this over here is 13/9 times this guy. And that's what I'm going to have. So we'll go back to black. What I'm going to have is 13/9 times the integral of e to the 2t cosine 3t is equal to 1/3, and the only stuff on the right-hand side, this all stays the same. Nothing changes here. I'm just recopying it. This stuff is just joined and moved on to the other side. 13/9 times this guy, so I have 1/3 e to the 2t sine 3t plus 2/9 e to the 2t times cosine of 3t. Now I'm almost there. I have an ugly constant out here, so I need to get rid of this and kind of multiply by something to get rid of that constant, and then I'll actually have the answer to what I was trying to find. So what I need to do is multiply by the inverse, multiply by 9/13. So at the end, I'm going to get 1 on the left-hand side. So I have integral e to the 2t cosine 3t. Okay, that's the integral I was trying to find, dt, is equal to. Let's multiply by 9/13. If I multiply by 9/13, then 9 divided by 3 is just going to give me 3. So I'm going to have 3/13 right there. I'm going to have 3/13, and then this stuff stays the same. E to the 2t sine 3t, okay, plus. If I multiply by 9/13 here, the 9 is going to go out with the 9, so I'm going to have 2/13 e to the 2t cosine 3t. Make sure you understand that. The only thing I'm doing is multiplying by 13/9 to get this integral by himself. When I multiply by 13/9, the 9 is going to go with 3, giving me a 3 on top, so I get 3/13 e to the 2t sine 3t. And then over here, multiplying by 9/13, 9 goes out with 9, so I get 2/13 e to the 2t cosine 3t. Now, what do we have here? Integral of this guy right here is equal to something, which we have now. And this integral is actually what we're trying to solve for. That integral that we just found is equal to this integral that we were trying to calculate. Even though integration by parts seemed to fail at first, it actually succeeded because once we did it twice, we realized we had the same integral on the right-hand side. We combined them, so now we know what the value of that integral is equal to, and we have written that down. So k of t, which is integral to our solution, is equal to 1/2 times the integral that we just calculated. Now, I could have kept 1/2 wrapped up in here, but it's just another constant. So I elected to find the integral first, multiply by 1/2. That's going to give us k of t. So all we have to do now is say that k of t is equal to 1/2 times this integral. We just said that. So 1/2 times each of these terms. So what's 3/13 times 1/2? It's going to be 3/26 e to the 2t sine 3t. Plus, what do we multiply 1/2 over here? The 2 is going to cancel with the 2 on the bottom, so we'll have 1/13 e to the 2t cosine 3t. This is k of t, ladies and gentlemen. What we have is 3/26 e to the 2t sine 3t plus 1/13 e to the 2t cosine 3t plus, don't forget, a constant of integration. And so now really we have the answer. So here we found the homogeneous solution of the equation, and we let this parameter vary, k of t. So the final solution is the current is equal to k of t times e to the minus 2t. So let's go ahead and do that. What we're going to have is, don't forget that I of t is just going to equal k of t times e to the minus 2t. So we just multiply by k of t. So what we're going to get is I of t is equal to all this stuff times this guy. Now let me do a little bit of a cost saving measure. All we're going to do is multiply this times e to the minus 2t. So you can kind of do that. I mean, you could write it all out again and then simplify it, but really it's pretty simple. So we'll have 326. All right, now what is this term times e to the minus 2t? Well, this is going to annihilate. This is going to give you e to the 0, giving you 1. So all you're going to have is sine of 3t. Plus this term, you're going to have 1 over 13 multiplied by, well, you're going to have this term multiplied by this term. So e to the minus 2t again is going to cancel, giving you e to the 0, giving you 1. So you're only going to be left with cosine of 3t plus constant of integration. Plus this constant of integration also multiplied by e to the minus 2t. And ladies and gentlemen, after all of that work, this is the solution to the non-homogeneous version. Now, we were not given an initial condition for this problem, so this problem still has some constant. You would have to specify the current at time 0 or the current at time 4, some kind of initial condition to nail down what C is, but this is really telling us everything we need to know about how this system is behaving. Now, when we look at it, let's look at the solution, just like we did last time. We have some constant, 3/26 times the sine, plus some constant times the cosine, plus some constant times e to the minus 2t. Well, we can see that this guy, because I have an exponential that has a negative sign there, it's going to cause this term to fall away as we go to 0. So this guy, let me use a different color here, this guy is the transient solution. So it's important, but it really only manifests itself in the beginning of, right at t, close to t0, and then after that, this term is going to drop away completely. Now, everything else left over, this is called the steady state solution. And this is what's going to dominate the whole situation as we go on towards infinity, as t goes on to infinity. And in fact, if you were to plot this, right, which I've done, right, then what you'll have is t, and you're plotting I as a function of time. What you're going to see, and again, I'm not going to be exact, it's not my intention to be exact, but it basically looks something like this. It starts out something like this, something like that, right? I don't think I quite have this valley exactly right, but you get the basic idea. So what you have is you've got some startup transient, it doesn't go too far below, and then it settles out. So then ultimately, as time goes on, this term has fallen away, and that was what was happening in the beginning here that was dominating everything. This guy, this cosine plus this sine, is really dominating the solution as we go forward, as we go on to infinity. And it makes sense that trigonometric functions would dominate the final answer because we're driving the circuit with a cosine. We're driving the circuit with a cosine. So as time goes on, this cosine is really going to be what dominates the solution. Now, one thing I do want to tell you, when I plotted this equation, I had to choose some value of c because you have to have some initial condition in order to really start it. So I chose c is equal to 1. And so when I plotted the guy, but if you had a different initial condition, the starting point of the graph might look a little different, but the general shape is really what I'm trying to show you, is that you've got some startup behavior, it dies out, and then you really got the rest of the solution completely dominated by everything else. And so in that regard, it's really similar to our previous problem where we had just a 12-volt source there. We had a transient startup, and then ultimately the steady state was a constant current going through there because it had a constant voltage driving the circuit. Here, the transient is something different, but the steady state is some kind of combination of cosine and sine, which is a periodic function because my voltage source is a periodic function. So the long-term nature of what's going to happen with a circuit, could be a spring system, could be any other system. If your input function is some kind of a sinusoid, chances are your long-term solution as you go off to infinity is going to be some kind of sinusoid, I guess is what I'm trying to say. You may have startup transients right when the system starts, reacting to the system, to the stimulus as it starts up, but those will a lot of times die out and be dominated by the long-term behavior. You can see with this example, it's really lengthy. But the process is bulletproof and the same as what we did before. We had a circuit, we wrote Kirchhoff's law, and then basically what we did is we wrote Kirchhoff's law, which is voltage drops across these components equal to the source. We solved the homogeneous version of the equation, right? And then that allowed us to write the current as a function of time like this. Now this is just a homogeneous solution, so this is how the circuit reacts without a continuous stimulus. If you just inject current, let it go and see what happens, you can see that it decays off, and that makes sense. So we vary the parameter here, plug that solution into our original differential equation, and we find that we have k prime of t that we need to integrate, and this really became the bulk of the work. This integral was kind of a monster, and if you have a table of integrals, or if you can use a calculator, then just do it that way. But otherwise, use the tools that you have. Did integration by parts once, and we got this. Did integration by parts again on that, and that gave us this. We noticed that we ended up with an integral that was exactly the same as what we started with. So when we write it over again, and I erased a little something by accident here. When we write it over again, this guy times, don't forget your constants out in front. You got to be careful about that. 2/3 times this integral, but this integral is equal to this. We have to keep your constants straight. When you do it and distribute it all in there, you'll see that this integral is here and this integral is here. And that allows you to algebraically subtract it to the other side. And when you do that, you can say that that integral that you were trying to solve for, right, is equal to the other stuff that was in the equation. So we get rid of the constants out in front. That integral that we were trying to find was equal to this stuff. So then k of t was just 1/2 times that integral from what we had defined before. So this is what k of t was. Stick k of t back in our solution for I and do the multiplication, get rid of a lot of these exponentials, and we end up with something like this. And you should expect one constant of integration in the end because it's a first order differential equation. If we had an initial condition, we could find that, but this problem was long enough, we didn't need to do that. And so we find out that we've often have these transient solutions and these steady state solutions. I'm Jason. It's a mouthful. I hope you've learned something. Half the problem with these things is just understanding how to write the differential equation. And then once you think you get to the end, sometimes you run into an integral that you rack your brain against. It's normal. It's not something that is unexpected. Just keep your chin up, work a lot of problems, practice your calculus skills, and you'll do just fine. Now that concludes volume 1 of the differential equations tutor, and here we've covered the first order differential equations, and you can see that even with just first order systems, the problems can get lengthy, but very practical. We've done some work with circuits and temperature and other things that are really practical, that have real world use, just first order equations. So practice these techniques, get good at them. A lot of times the system that you study in nature really is first order, and you can really learn a lot from that. We go on into the subsequent volumes, we'll learn second order and even third order and higher differential equations. There's a whole different batch of techniques that we use to tackle those types of equations. And in fact, once you get to high enough order and even simple second order equations, you can't even solve them at all without using a computer. So this is not something that you should find is just going to come to you overnight. It takes a lot of practice. So get good at these techniques. These techniques will be used later on in building upon them. So don't flush them. Make sure that you really understand what's going on here. Go into the second order equations in the next volume of the differential equations tutor, and you'll have lots of tools in your tool belt to tackle solutions in engineering and physics and chemistry and all branches of math and science. Learn anything at mathandscience.com.